Good morning, good afternoon, and good evening, depending on when you might be watching this. My name is Kevin Hobbs, and I'm a geologist. I work for the New Mexico Bureau of Geology and Mineral Resources in Socorro, New Mexico. Geology is the field of science that studies the Earth's internal structure, what it's made of, its history, and the forces that act upon it. And along with my colleagues, I get to do a lot of that in my duties here at the New Mexico Bureau of Geology. The Bureau was founded in 1927 by state legislation, and we serve as the Geological Survey for New Mexico. We're tasked with getting accurate information to the citizens and governments within New Mexico. We conduct research on the geological processes acting on our state. We serve as a repository for geological specimens, and my favorite part of the job, we get to do outreach to help students and interested citizens learn more about geology and about the history of the state where we live. For this year's Explora Science Fiesta Week, I'm thrilled to have the opportunity to be able to tell you about one of my favorite geologists, a man named James Hutton. Hutton lived in Scotland way back in the 18th century, nearly 300 years ago. And one of his ideas was so instrumental, so fundamental to the development of geology as a legitimate science that he's often called the grandfather of modern geology. He studied a geological feature called an angular unconformity. Don't worry, we'll explain what that is in just a moment. His angular unconformity was on the eastern shore of Scotland, on the North Sea. Fortunately for us, we have loads of examples of angular unconformities that rival the one that Hutton studied right here in New Mexico. And although it's a virtual field trip, I want to take you on a field trip to one of my favorite unconformities here in San Lorenzo Canyon in Socorro County, New Mexico. This unconformity is on public land, and it's only about 2 miles from Interstate 25. You can reach it in a passenger car, and I hope at some point you will. So let's take a moment to learn a little bit more about James Hutton, who he was, and how it came to be that he contributed so much to our understanding of the history of Earth. Hutton was born in 1726 in Scotland. Even though he was born in Edinburgh, at the time Scotland's largest city, he spent most of his time to the southeast of Edinburgh, in this farming country. He was a chemist, a medical doctor, and a farmer. In fact, his farm is still used. But as a geologist, he liked to spend the time just to the north of his farm, on the coast of the North Sea. His most important discovery came here, at this promontory called Sicker Point. You can still visit there today. Hutton sailed there from nearby Dunglass in the 1780s, where he saw an angular unconformity. Hutton likely sailed out of a harbor like this one. This is at a place called Cove, Scotland. And you can see these beds of rock projecting out into the sea. Here's the spot that Hutton was aiming for. This is Sicker Point, viewed from the land above it, about 150 feet above the sea. Hutton likely stood at this very spot. He saw the beds of sedimentary rock projecting in the ocean, but he had a hard time getting access to them from above, which is why he sailed from Dunglass. The rocks here also are used in many of the walls and fences around this area, so Hutton had seen them up close, but not in place, until he reached there by boat. And this is what he saw. This is the unconformity at Sicker Point. Many geologists now call this Huttons Unconformity because of the role he played in describing it. Beneath the unconformity, in the bottom half of this photograph, are vertical gray beds of a sedimentary rock called greywacke. Above the unconformity, in the upper part of this photograph, are reddish beds of Devonian sandstones. In fact, this rock unit is called the Old Red Sandstone. Hutton had studied the deposition of sediment in the beaches and rivers and lakes of Scotland before he ever came up with this hypothesis. And he knew that the deposition of sediment was a very slow process. So to build up this much sediment, he postulated, must have taken a very long time. Not only was this sediment built up through deposition, that lower sediment, the vertical Silurian greywacke, was then deformed. It was then eroded, and the younger sediment, that red Devonian sandstone, was deposited on top of it. Since that deposition, it has also been tilted and eroded. If you visit Siccar Point today, you'll see interpretive signs like this one, telling you about James Hutton and the geology at Siccar Point. Here's another one, explaining who James Hutton was, but especially it does a good job explaining how the unconformity came to be. So let's take some time to try to understand this, and I'm going to use the visuals from this sign to do that. First, the oldest sediment was deposited on the bottom of a sea. These sediment beds were initially horizontal. After that, those beds were deformed, folded, and uplifted during a mountain building event. Those flat-lying beds were no longer flat. The rock layers were then eroded, creating that jagged surface. And on top of that jagged surface, 65 million years after they were first deposited, new sediment was deposited in new beds that themselves were initially horizontal. That new sediment was then compacted into rock layers, and it was tilted and eroded, creating the unconformity we see today. The reason that Hutton's idea that he developed at Siccar Point were so groundbreaking, the reason that they remain fundamental to scientists today, is that they helped geologists understand that the time required for the creation of rocks and unconformities and other geological features is a very long time. Remember, when Hutton was working, many philosophers and even natural scientists in Europe and in the Americas were subscribers to the idea that the Earth was only about 6,000 years old. Some even believed that all rocks on Earth were created during Noah's flood some 4,000 years ago. However, by observing processes like the erosion of rocks on the Atlantic coast, processes like the deposition of sediment on seashores, in riverbeds, and in lakes in Scotland, Hutton postulated that more than 6,000 years was required for the creation of these features. In fact, he said that time had no vestige of a beginning and no prospect of an end. The numbers were so big, he said, I can't even imagine them. The Scottish people are rightfully very proud of James Hutton because of the contributions that he made to the fields of geology, chemistry, and medicine. In fact, they ensconced him here in the Scottish National Portrait Gallery with a life-size statue. I like to think that somehow Hutton is getting some satisfaction from knowing that people 300 years after his birth are still looking at him, carved out of red sandstone, the same type of rock that he studied at Siccar Point and so many other unconformities throughout northern England and Scotland. If you ever find yourself in southern Scotland, head to the small town of Coburn's Path, and from there walk just over a mile to the east along the James Hutton Walk. The local town council has put this walk together. It's a nice guided trail with informational placards and incredible views of the Scottish countryside and the North Sea. They did this to honor the ideas and the life of their native son, James Hutton. The walk ends, of course, right here at Sicker Point, just about a mile east of Coburn's Path. This is the site of the world's most visited, best described, and in many people's opinion, best angular unconformity. Once you're there, it's easy to see how Hutton and his contemporaries were overcome with joy at figuring out this grand problem. If you can't make it to Scotland, don't worry though. We have loads of wonderful angular unconformities right here in New Mexico. Let's take a look at one of my favorite New Mexican angular unconformities at a place called San Lorenzo Canyon in Socorro County. And here's the angular unconformity at San Lorenzo Canyon. Just like Hutton's famous unconformity at Sicker Point, this one also has deformed sedimentary beds below the unconformity and relatively flat-lying beds above the unconformity. In this photograph, the deformed sedimentary beds below the unconformity make up the majority of this vertical rock face, which is about 10 meters tall. That's about 33 feet. The upper 20% or so of this outcrop is flat-lying, younger sediment. Let's take a closer look at these sediments to understand better what the environments were like when they were deposited. My hand right now is resting on a bedding plane. That's a surface that was originally flat, and it was originally the surface of the earth, back when this sediment was first deposited. On this surface, there's this wavy structure, and these are sand ripples. Now, you might have seen sand ripples in the bed of any sandy stream or arroyo in New Mexico today. These are no different. The only thing is that these are very old, about 16 or 15 million years old. They were deposited by a flowing stream back in the Miocene epoch. Interpreting structures like these and the environments that they form in is one of the things that allows us to make sense out of this bigger picture that we're talking about today, this angular unconformity. And it's interpreting these differences in environments that allowed James Hutton and allows a geologist after Hutton, including right up to the present day, to make important statements about the evolution of the history of Earth. Here's an up-close view of that same bedding plane from the last frame. You can see the ripples in the surface, and in the sand layers beneath it that are in the frame now, you can see these very fine beds of sediment. Some of these are only a few millimeters thick. As we zoom in, you can see they're made of individual grains of sand. Some of the darker beds are made of finer grained material, mud and silt. Here's the shadowy surface with those ripples once again. And as we go up into younger rocks, you can see there are some larger clasts, like this pebble. Here we are at the beds below the angular unconformity. So that surface separating these dipping beds from the flat-lying beds on top of them is about 10 meters above me, above my head. I'm at the foot of that cliff that we saw in the earlier footage. And the reason I want to show you the rocks right here is because they express so beautifully the nature of these beds. A bed is the fundamental unit of sedimentary rocks. Here we have different layers of beds. Each of them is dipping, parallel to my hand right here, about 30 degrees off to the east. So we describe the dip direction in the way that they go down. These are pointing down that way, which is to the east. Most of these beds, and most beds in general, in fact, all over the world, are relatively planar structures. That means they exist in 2 dimensions without much variation. However, there is variation. Look at this bed. See how it's wavy? So the general rule is beds are planar, but there are always exceptions. This bed right here, this darker, redder bed, is made up of a fine-grained sediment called silt. It feels very smooth. It was deposited in some sort of wetland environment, probably a pretty low-energy environment. The water was not moving with very much swiftness. It represents a single depositional event, meaning the time that this was deposited. Then deposition stopped. Sometime later, this next bed above it was deposited. This bed is sandy. I wish you could feel this. It's gritty. It feels just like sandpaper. It takes more energy to move those large sand particles than it takes to move these fine silt particles. So the environment where this was deposited must have changed just a little bit. We're not talking about a change from some lagoon to a raging river, but just a little increase in stream velocity. After this sand was deposited, deposition stopped again. Then another bed was deposited, then another, on, until we ended up with quite a great thickness of this sediment. The formation that this sediment belongs to is called the Popatosa Formation. It outcrops all up and down these low hills on the the west side of the Rio Grande in Socorro County. Its total thickness is measured in hundreds of meters. This is an immense volume of sediment. And think, all of that immense volume was laid down in tiny little beds, one at a time. But if you give it long enough, it can stack up to great thicknesses. When these beds were first deposited, they were flat. They were horizontal, very, very close to horizontal. Obviously, that's no longer the case. There's been tectonic deformation that has moved these from horizontal to tilted. And it's the interpretation of that moving and the time required for that moving especially that led James Hutton to his big idea at the Unconformity at Siccar Point, Scotland. The time required to move these beds here in Socorro County is also an important consideration for the geologists like me and my colleagues at the New Mexico Bureau of Geology who attempt to interpret the meaning, the history of these rocks. One of the things that it's important to remember about angular unconformities, the development of the idea, the science of geology, and the work that James Hutton was doing back nearly 300 years ago, is that he was not working with a really advanced technological set of tools. In fact, the tools that he had are those available to nearly any elementary school classroom today. Hutton would have been shocked by the technology that exists, say, in a typical American high school chemistry lab or physics lab. What he did have was the power to observe. And observations of current geological features, like this one right here, are what led to many of Hutton's greatest contributions to our understanding of geology and our understanding of how the world works, how it came to be what it is. Hutton observed things just like this. Here's a bed of sediment. It's about 20 or 30 centimeters thick, and most likely it was deposited during this summer's monsoon storms. This is the summer of 2021, and we had a really wet, powerful monsoon year this year. My house down in Socorro, which is only about 15 miles away, we got about 8 inches of rain in just 2.5 months. The yearly average is only 10 inches, so this was a much wetter than typical monsoon. And all of that rain and all of that water moving through the landscape did a lot of work. It deposited a lot of sediment. Sediment was eroded from somewhere farther upstream. Something that's important to note, something that Hutton noted so long ago, and in fact someone about 150 years before Hutton noted, a man named Nicholas Steno, noted that when sediment is first deposited, it's horizontal. Beds, like this one right here, always every time Steno observed a freshly deposited sediment, every time that Hutton observed it, every time that I observe it, and every time that any sedimentologist working in this field observes it, it's always horizontal. There are small fluctuations like ripples that we saw at the Unconformity, but by and large, these beds are horizontal. So when we see beds of sediment that are not horizontal, but instead tilted, like the ones at Huttons Unconformity at Sicker Point, or the ones right down this arroyo here in San Lorenzo Canyon, we know that something has changed them. Geologists call that change deformation. When you take things that started flat and tilt them, we call that deformation. In order to get any angular unconformity, you have to have deformation. The one here at San Lorenzo Canyon, the one at San Isidro northwest of Albuquerque, the one at Huttons Unconformity, the famous one in Grand Canyon in Arizona, USA, the famous one at Ouray, Colorado. Any angular unconformity you can think of, any one you'll ever see, exists because there has been deformation, movement of horizontal beds to not horizontal. How much they move, over what type of time period they move, the forces that move them is variable, but they all moved. The forces that move them almost always are tectonic forces, the movement of continents, the stretching and squeezing of Earth's lithospheric plates, that's the outer layer of the solid Earth, is what can take something that started flat like this, make it not flat anymore, deform it. Once you erode off the top of that, deposit more flat sediment on top, and what have you got? An angular unconformity.
You know, James Hutton spent a lot of time in Scotland back in the 1700s doing exactly what we've been doing today. Exploring the countryside, looking at the rocks that were available in outcrop, and formulating ideas and hypotheses about how they came to be. Once he finally wrote his ideas up, one of the quotes that always sticks with me from his writing is this: Hutton thought that time had no vestige of a beginning and no prospect of an end. This was a controversial idea, in 18th century Europe. There are members of our society who still find this controversial. And, in fact, 25% of Americans reject it outright. Hutton had a friend and contemporary named John Playfair, another Scotsman. Hutton and Playfair often visited field sites together, and the two sailed to Sicker Point once, and they visited the angular unconformity there. Hutton shared his ideas with Playfair, and Playfair was a very skilled writer. After that visit, Playfair wrote that his mind seemed to grow giddy by looking so far back into the abyss of time. Maybe I haven't been able to make your mind giddy with this angular unconformity. However, I hope you've learned something. I hope maybe you have a new tool with which you can appreciate, explore, observe, and learn about the natural world all around us. You know, science is never finished. We're never done with what we do. There's always more around the corner. There's more observations to make, more hypotheses to test, more discoveries to uncover. There are few places on Earth better than New Mexico to explore geology in the field. All of this is public land. It belongs to you just like it belongs to me. I hope you get out there and explore it. Make observations, ask questions, and always keep learning.